For this first one, what things do you need to include to have something be considered a solution? A solvent and a solute, okay. What other things?
Homogeneous.
Say again? Homogeneous for sure. So we need a homogeneous mixture. Does it matter what the states are of those things? No, could be two nonpolar things. No, states. When I go to mix them together, do they have to both be liquids? No, I could put table salt into water and get a solution. Or, so does that mean one of them has to be a liquid? You could have two solids. We talked about the copper and the zinc when you guys made brass last term. So if you mix two solids together, you would need to liquefy them for a time period, but then after they've been liquefied and they form their homogeneous mixture, then they're solids and they're fine. So that counts. We're just looking for a homogeneous mixture of two or more substances. And we have a solvent and solute or solutes. The next one, how about that solute and solvent? How are those two things related to each other? The technical definition, the solvent, there's more of it. That's it. Whichever one you have more of, that's the solvent. Normally we think about that being the liquid, like a water dissolving sugar or dissolving salt, but whichever one there is in greater quantity is the one that's going to be considered the solvent. So our example we had with the alcohol was like vodka was 20% ethanol and 8% water. So then in that case, the solvent would be the water. But in that rum, it was 75% alcohol and 25% water, and in that case, the ethanol would be the solvent and the water would be the solute. I just read something on the paper about Hood River Distilleries. Their vodka, HRD, was the most sold vodka in Oregon last year. They sold 250,000 gallons of it. That's a lot of bad vodka. Describe and explain what happens to a soluble solid as the temperature increases. All right, so what happens to the solubility of a solid as our temp goes down? So the temp of the solute decreases. How much solvent can I get shoved in there? As my temperature of my solution drops, what about the solubility? It also drops. So we need to think about like a salt crystal and its water molecules going in and pounding away at the salt crystal's ions, separating them out. And if they're at a higher temperature, that gives them more energy, and so they're more easily able to knock those things free, to dislodge them. Describe what happens to the solubility of a gas as the temperature of the solution increases. All right, so this time I'm going to have a temp increase. And what's my solubility of my gas? It also decreases. And what's the reason behind that? Gases simply have enough energy to leave. They just go up to the surface and they go into the atmosphere. You can't have that happen with table salt, right? I can't have table salt at a higher temperature in the liquid just go up to the surface and turn into a gas, because it doesn't turn into a gas at normal temperatures. All right, solvent. Kinetic energy increases for that one. All right, let's talk about molarity. So the definition for molarity is going to be the moles solute divided by the liters of solution. Not the liters of solvent, the liters of the total solution. And so then in that case, my units are going to be moles over liters. All right, so let's, what is the concentration reported in units of molarity when 140 grams of potassium iodide is added to 100 milliliter solution? Okay, we want concentration, and so the concentration units that we're looking for are moles per liter, because it said molarity. So we need moles and we need liters. And in this problem right here, we've got grams and milliliters. So we know we can turn the milliliters into liters, so we have half of it. And we should know we can turn grams into moles. Okay, so I want moles per liter. So my gram number, my 140 grams of potassium iodide will go in the numerator. And then I'm going to get rid of that gram number by using the grams per mole. And so does somebody have a mass for potassium iodide? 165.9945. That doesn't look so good. 9945 grams of potassium iodide for every 1 mole of potassium iodide. Okay, so my grams of Ki are gone, and so I've got my moles of Ki. So I got half of it, and then I need the denominator to be volume, so I'm going to put my 100 milliliters down here, and then I'll put 1,000 milliliters is 1 liter, and I can get the milliliters to cancel. And then when I do that, I've got the 2 units that I'm looking for, which are moles and liters, and those are the only ones left. And so then my answer will be in moles per liter. And does somebody have an answer? Anybody? That looks good, because we're going to end up multiplying that. That number will be less than 1, but then I multiply it by 10. Yeah, that looks good. What are the sig figs? What does it work out? 8. Just 1 sig fig, right? Because in that 100, there's just 1. So I probably should have put a decimal place in there, but regardless, 1 mole per liter, or 8 mole per liter, sorry. Okay, will potassium iodide dissolve in a 20 and 10 degree solution? So to answer this question, you would have needed to go to the solution notes, and the solution notes could have gone to this little table here, and on this table we're talking about potassium iodide at 20 degrees. So at 20 and 10, is that right? 20 and 10, so then I'll take this line up, and so we're talking about that spot right there, and we're talking about that spot right there, and we had 140 grams. So at 20 degrees, what's the question? Will the potassium iodide all dissolve at 20 degrees? So will it be dissolved? Yeah, how much can you fit at 20? Yeah, it looks like 145. So the answer for this one is yes, because you can fit about 145 grams at that temperature. But at 10 degrees Celsius, the answer is no, because it's, what do we got there? 135, something like that. Because this will only fit 135 grams. So this solution right here, what would we call this solution as far as saturation goes? This one here is unsaturated because I can still put 5 more grams of solution in there. So unsat over here, and this one over here, it's saturated, and it's saturated to the point where you actually have too much. So this one, this guy, it's still a solution because it's all dissolved, but is this a solution at 10 degrees? It's not, because some of the solid is sitting at the bottom. About 5 grams of it is sitting at the bottom, so technically it's not a true solution. To make it a true solution, you could just decant it. Do we know what that word means? Sometimes it's used to talk about drinks and whatnot, but what would decant be? You use a decanter to pour stuff off of a liquid when there's solid at the bottom. So if you've got some sort of mixture and the bottom of it you don't really want, so it could be coffee, right? You use a French press, and that's like a mechanical decanting process. You don't want to have the coffee grounds in your coffee cup, so you push into the ground and then you decant the liquid off the top. And so in this case, if I took this 10-degree solution, I have this solid at the bottom, and then I could dump some of the liquid into another container, and now this container is a solution because there's no solid, because it was stuck at the bottom of the other container. And that's usually how a person makes a saturated solution. They over-saturate something, and then they just dump off the top part of it, and then the excess solid is sitting in the other container. Makes it easy. Explain how you would make a 250 milliliter 0.35 molar sodium hydroxide solution. So this is more than just math. We want an explanation for this one. All right, but let's do the math first. So I need to know, I know I need 250 milliliter container, but I need to know how many grams of sodium hydroxide to put into the container. So what I need are grams for this one, and what I have are 0.35 moles of NaOH per liter. So I need to get rid of the moles and the liters, and I can take this 250 milliliters and turn it into 0.25 liters, and now my liter number is gone. But now I need to get rid of the mole number and turn that into grams. So for every 1 mole of NaOH, we're looking at, is it 39 point, does anybody have that? What? It's 39.
Oh, sorry,
39.998. Yeah, it's an H, an O, and an Na, so that's 23 and 1 and 16, so about 40. All right, and then when we do this, we get about 3.5 grams of NaOH. So then the question wants us to explain how. So there's lots of different orders you could do this in, but we'll do it this way. So first I need get 250 milliliter vol flask, and then get 3.5 grams of NaOH. And number 3, add NaOH and half fill with deionized water. Mix. And next, fill near top. Or let's go with near the line. And then we will use dropper to the line. And then let's do one more, 7. Invert. That looks terrible. So just flip it over once, and that'll take care of mixing the stuff that's in the neck with the stuff that's in the rest of the flask. Okay. We're going to do molarity and molality. So the contrast between these two is this one is based off of volume, and this one is based off of mass. This one is more accurate, but also more expensive. And it's also not temperature dependent. So there's lots of reasons why the molality one is better than the molarity one. But in reality, we usually don't need to be that accurate, so we don't bother with it, because we don't really want to buy a really expensive scale that could handle all that excess weight. Any questions? No?